This is part 8 of the series Logarithmic, Exponential, and Other Transcendental Functions. In the last video we ended with this two-part example, and I want to go ahead and work a couple of more examples just to make sure we've got this idea of derivative of an inverse function down. So let's take a look at another example. Here we want to find the derivative of the inverse of f evaluated at 26. So like we said in the last video, we know that the domain of the inverse is going to be the range of the original function. So we need to find out what value of x generates a range value of 26 for this function. That's the first thing we're going to do, and then move through the rest of the solution. Here I just set the original function equal to 26, and then we solve for it. We move the 26 over, and then we find out what values of x will generate that 26. Well, this is a difference of 2 cubes, and so that factors out to this, the cube root of this, that sign, the cube root of that, times this guy squared, this times this with the opposite sign, so that's 3x plus, and then this piece squared, which is 9. Now you can clearly see that this piece has no real solutions because all the coefficients are positive and this never touches the x-axis. So the only solution is x equals 3. That means that the x value of 3 will generate a 26 on the outside. And that tells us that f inverse at 26 is 3, because the range of this is the domain of this, and the domain of this is the range of that. And again, we found the value of an inverse at a value without actually finding the inverse. Then we want to find the value of the derivative of that inverse at 26. And that brings up our faithful formula, 1 divided by f prime of f inverse at that original value. So we know that this is 1 over f prime of 3, because we already know that f inverse of 26 is 3. We just found that. That's all we need now is f prime. So here, if we take the derivative of this, it gives us this guy. So we just evaluate this derivative at 3. And if we put a 3 in there, we have 3 times 3 squared. 3 times 3 squared. That comes out to 1 over 27. So a fairly straightforward example there. Let's go ahead and look at another one. Here we want the derivative of the inverse of sine x evaluated at 1/2. Again, the domain of the inverse is the range of the original. So we're going to find out what x values generate a sine equal to 1/2 and move from there. So we set sine x equal to 1/2. We solve, and that gives us x equals pi over 6, because we know that sine of pi over 6 is 1/2. But now you might say, well, yeah, but 5 pi over 6, sine of 5 pi over 6 is also 1/2. However, consider this. What we're dealing with is sine on a particular interval on which it has an inverse function. And if you take a look, this is the sine function, but only in the interval of negative pi over 2 to pi over 2 does sine have an inverse function. And that's because this is arcsine, and its domain, its range, is negative pi over 2 to pi over 2. So you can see, again, the domain of the original is the range of the inverse. So we have to consider only the values of sine on which it has an inverse function, which is negative pi over 2 to pi over 2. Therefore, pi over 6 is the only one that has a value of positive 1/2. Therefore, f inverse at 1/2 is pi over 6. So when the input of the inverse is the output of the original, pi over 6 is the output of the inverse. Now let's go and find our inverse. F inverse, the derivative of F inverse at 1/2 is equal to 1 over F prime of F inverse at 1/2. We just said that F inverse at 1/2 is pi over 6. So this becomes 1 over F prime at pi over 6. So now we need the derivative of sine. The derivative of sine is cosine. So here's F prime of x, cosine. So we evaluate cosine at F inverse of 1/2. And that's this piece. And again, F inverse at 1/2 is pi over 6. So this is 1 over cosine of pi over 6. Cosine of pi over 6 is square root of 3 over 2. And that equals 2 over the square root of 3. And that's our final value. All right, let's go ahead and look at one final example. Here we're looking for the derivative of the inverse of this function evaluated at 2. And so we're going to set this function equal to 2, just like we did in the last 3 examples, and solve from there. So we set f equal to 2, and we square both sides, and therefore x equals 8. And that's the only value that we have, so we know that f inverse evaluated at 2 is equal to 8, for the same reasons of the inverse. The domain of the inverse is the range of the primary function. Now let's take the derivative of the original. F prime is 1/2 x minus 4 to the negative 1/2, which comes out to this guy here, 1 over 2 square roots of x minus 4. And so the derivative of the inverse evaluated at 2 is 1 over f prime of f inverse at 2. Missing a parenthesis there, but that's okay. And we go ahead and substitute in. So it's 1 over 2 times the square root of x minus 4, but x is being replaced by f negative 1 of 2. And that's going to be this guy here eventually. But because this is 1 over 1 over, this denominator is going to actually end up in the numerator, basic algebraic process. So we have 2 times the square root of f inverse evaluated at 2, which is just 8 minus 4. This is 2 times the square root of 8 minus 4, which is 2 times the square root of 4, which is just 4. So it can get a little bit involved, but just understand the concept of the reflective property of inverses, and it's not all that difficult. That covers inverse functions for now. We're going to come back to inverse functions in greater detail when we deal with trigonometric inverse functions. But for now, we're going to move on, and we're going to start looking at exponential functions, both from a differentiation standpoint and integration. So let's look at exponential functions. Let's start our discussion of exponential functions with the definition of the natural exponential function. The inverse function of the natural logarithmic function, f of x equals ln of x, is called the natural exponential function. And it's denoted, if f is ln of x, then f inverse of x is e to the x. And we saw that in this picture before when we were talking about inverses in general. That was the example I used. The natural log of x is here, and e to the x is here. So this is the inverse of this. And therefore, y equals e to the x if and only if the natural log of y equals x. And this is all based on the idea that natural logs, logarithms in general, are simply exponents. So you'll notice this is log to the base e of y. The base is e. The base is e. The exponent is a logarithm, so that's an exponent. There's the exponent. And this is the object. So these are inverses of each other. In summary then, the natural log of e to the x is equal to x, because this is log to the base e of e equals 1. This is the power rule of logarithms here. And in the same vein, e to the natural log of x is also x. Also, you can look at an inverse version of this, y equals a to the b. If that's true, then y is also equal to e to the ln of a times b. This is just taking this process and tacking on a property of exponents. So you can see that because x equals e to the ln of x, then a is equal to e to the ln of a. So I just replaced a with e to the ln of a and raised that to the b power. So this is raised to the b power. And then when you take something with an exponent raised to an exponent, you just multiply the exponents, and that's what I did here. So that's what this is all about. It's just manipulating exponents. This is going to be a very, very important concept right here. This property is going to help us greatly when it comes to differentiation and integration of exponential functions. Let's go ahead and work through a few examples of some exponential functions just to refresh us with the ideas of logarithms and exponents. So we're being asked to solve 7 equals e to the x plus 1. Now there's a couple of ways to do this. Probably the most straightforward way is just to take the natural log of both sides and work from there. Here I take the natural log of 7 and then the natural log of that entire right side. And you can see that these properties up here are coming into play. The natural log of e to the x plus 1 is simply x plus 1. So this becomes ln of 7 equals x plus 1. We subtract 1, that equals x, and that's approximately 0.9459. Alright, let's take a look at another example. So this is just an inverse example. We're already given a natural log of something. So what I'm going to do is I'm going to use these as exponents of a base e. So I'm just going to make this e to the ln of 2x minus 3 and e to the 5. Again, taking advantage of the natural logarithmic exponential properties, e to the ln of anything is that thing. And so the e and ln cancel each other out, so to speak. And on the right side, we just have e to the 5. Then we add the 3 to both sides and divide by 2. And x equals e to the 5th plus 3 divided by 2, which is approximately 75.7066. Alright, let's take a look at one more example. So here we have something that's kind of a mix of issues. What I'm going to do with this guy is I'm going to multiply both sides by 1 plus e to the 2x and then divide both sides by 2. And that'll simplify things a little bit to first start out. So you can see 5,000 divided by 2 is 2,500, and then multiplying both sides by 1 plus e to the 2x gives us this. Then I just subtract the 1, and I'm left with e to the 2x. And I can do something similar to what I did on this example, and just take the natural log of both sides. So I kind of skipped a step here. I just took the natural log of 24.99 here. 2,500 minus 1 is 24.99. And then the natural log of e to the 2x is just 2x. And then I divide both sides by 2, and I get x equals the natural log of 24.99 divided by 2. And that comes out to approximately 3.9118. And if you're still uncomfortable with exponentials, logarithms, expansions, contractions, and the different log rules, I would strongly suggest that you practice some of those before moving on. And what we're going to do in the next video is we're going to start in on derivatives of natural exponential functions. So I'm going to go ahead and wrap up this video now, and I will talk to you in the next video.